Something just broke the rules of the solar system. Astronomers have confirmed that 32/Atlas, our third ever interstellar visitor, shifted its orbit in a way that can't be explained by gravity or even by powerful gas jets, contradicting everything we know about how comets move. This 8m-wide cosmic intruder is flying through at nearly 60 kilometers per second, but the usual suspects, sunlight and outgassing, just don't add up. If gas alone can't explain why 3I/Atlas defied gravity, what invisible force is at work? The stakes for astronomy and for our understanding of what enters our cosmic backyard have never been higher. So, how did this giant break the rule book right in front of humanity's best instruments? July 1st. 25 astronomers at the Atlas survey spot something that shouldn't exist. An object streaking through the solar system at nearly 60 kilometers per second. That's fast enough to escape the sun's gravity forever and more than double the speed of the last two interstellar visitors. But speed is just the start. 3Atlas is massive. Estimates put its diameter between 3 and 7 m, making it the largest interstellar object humanity has ever tracked. For perspective, Halley's Comet is just 7 miles across, and it's considered a giant by comet standards. Within hours, observatories worldwide scramble to confirm what's unfolding. The object's orbit isn't just hyperbolic. It's practically a straight shot through the solar system with an eccentricity over 6. That's not just rare. It's unprecedented. The trajectory, the speed, the size. Every aspect screams outsider. And as the data pours in, one detail stands out above the rest. As 3I/Atlas barrels toward the inner planets, its path begins to veer. Not wildly, not in a way you'd notice with the naked eye, but enough to set off alarms among the world's best orbital modelers. Here's where things get uncomfortable. The usual suspects: gravity, solar radiation, even the powerful jets of gas that can nudge a comet off course, can't fully account for what's happening. We're watching a cosmic heavyweight, a body with the mass to shrug off most forces, shift its orbit in ways that just don't add up. The math is off. The rule book, the one that's governed every comet and asteroid we've ever seen, suddenly looks incomplete. For astronomers, this isn't just a curiosity, it's a crisis. If something this big, this fast, can break the rules right in front of our best instruments, what else might slip through undetected? What else might we be missing? The stakes aren't abstract. They're about the limits of our knowledge and what it means when the universe throws us a curveball we can't explain. So, if you're the kind of person who wants to see the rulebook challenged, who wants to watch science catch up to the cosmos, now's the time to hit subscribe, because the story of 3I/Atlas is just getting started. And the next chapter could change everything we thought we knew about what moves through our cosmic backyard. Comets don't just coast through the solar system on rails. Their journeys are shaped by a constant tug-of-war between gravity and something far less predictable: outgassing. Picture a comet as a dirty snowball, frozen hard until sunlight hits. As it draws closer to the sun, ices trapped inside begin to vaporize. Gas jets erupt from the surface, sometimes in spectacular geysers, sometimes as subtle leaks. Each jet acts like a tiny thruster, nudging the comet this way or that. The effect is a bit like letting go of a balloon and watching it zip around the room, propelled by its own escaping air. Astronomers have spent decades turning this chaos into math. The Rosetta mission to Comet 67P/Churyumov-Gerasimenko proved just how powerful these jets can be. Rosetta watched as only about 10% of 67P's surface did most of the work, firing out plumes that not only changed the comet's path, but actually spun the entire nucleus faster or slower depending on which jets were active. With every orbit, these outbursts add up, shifting the comet's trajectory by measurable amounts. In fact, orbital models must include these non-gravitational forces, or predictions quickly go off track. The rules are simple in theory. The more gas a comet releases and the faster it escapes, the bigger the push. Scientists measure the amount of material, often in kilograms/s, flying off the comet and use it to calculate the force. For a typical comet, water iced as the heavy lifting, turning to vapor and blasting dust away at hundreds of meters/s. The result? A slow, Steady drift from the path gravity alone would dictate. Over time, even a small, persistent push can move a comet thousands of kilometers off its predicted course. But there's a catch. The effect depends on the comet's mass. A small lightweight nucleus is easy to budge. A large dense one is stubborn, requiring much more force to achieve the same shift. That's why the details. How much gas? How quickly? And from where on the surface matter so much. Every significant comet in history from Halley to 67P has obeyed this rulebook. If you know the jets and the mass, you can predict the motion. This is the playbook astronomers reach for every time a new comet appears. Gravity sets the stage, but outgassing writes the footnotes. For most comets, the math checks out. The jets explain the drift. The models predict the path. And the universe behaves as expected, with 3-2/Atlas. Though, that's about to be put to the test. Orbital prediction is supposed to be a solved problem. Plug in the numbers. Mass, velocity, solar gravity, planetary tugs, and the path of any comet or asteroid should trace out with pinpoint accuracy. For 3I/loss, the numbers refuse to cooperate. The calculated trajectory with an eccentricity of 6.141 sketches a nearly straight line through the solar system. A geometry that's rare enough to make even seasoned dynamicists pause. But it's what happens when you overlay the predicted path with the actual data that exposes the crack in the system. Each new observation comes with a timestamp, a set of coordinates, and a margin of error. Stack 100 of these, and a pattern should emerge. One that matches the equations, not just in theory, but in the real sky. Instead, the residuals, the tiny differences between where 3I/Atlas should be and where it actually is, begin to drift. Not by much, not enough to shout, but enough that the overlay doesn't quite snap into focus. For a normal comet, these gaps are quickly closed by adjusting for gas jets or dust ejection. With 3I/Atlas, those corrections fall short. The magnitude of the offset can't be erased with the usual suspects. The path veers almost imperceptibly, but in a way that persists across datasets and observatories. Engineers and orbital modelers run the numbers again. They factor in every known variable: the sun's pull, planetary perturbations, even the subtle push of solar radiation. The result is always the same. The model can't fully capture the deviation. The geometry of the anomaly is clear on the residual plots. The object's actual position diverges from prediction, not in random scatter, but in systematic way that suggests a force at work outside the standard playbook. This isn't the kind of error you can blame on bad data or a misaligned telescope. The global network of observatories from Mount Ayat to La all report the same subtle offset. The high eccentricity path of 3I/Atlas, so clean and direct in simulation, now carries a visible scar gap between theory and reality that no one can close. For the first time, the orbit itself becomes the main character refusing to play by the rules. The chemistry of the coma and the physics of outgassing are next in line for scrutiny. But the immediate problem is right there in the geometry. The rule book doesn't fit. The coma of 3/Atlas is not just a halo of light. It's a chemical fingerprint, and that print is unlike anything seen in the solar system. The numbers coming from the James Webb Space Telescope are impossible to ignore. For every molecule of water vapor in its coma, there are 8 molecules of carbon dioxide. That's an 8-to-1 carbon dioxide to water ratio. Off the charts, even compared to the weirdest Oort cloud comets. Most comets are water-dominated with carbon dioxide playing a supporting role here. Carbon dioxide calls the shots. It's pouring off the nucleus at rates measured around 129 kilograms per second, dwarfing the 6.6 kilograms per second for water. In theory, more gas means more push. Outgassing acts like a set of thrusters, each molecule a tiny kick. But even adding up every molecule, the math falls short. For an object this massive, estimates put the nucleus between 3 and 7 miles across. These jets don't have the horsepower to explain the observed drift. The momentum just isn't there. The chemical oddities don't stop with gas. Spectroscopy from the Very Large Telescope picks up something stranger. 22 distinct emission lines from atomic nickel. But iron is nowhere to be found. That's not normal. Nickel and iron usually travel together in cosmic materials, forged side by side in supernovae and mixed in meteorites. Here, nickel is out on its own, released into the coma by a process that seems to favor it over iron, possibly from exotic organometallic complexes or nanograins that break down under solar heating. The nickel production rate at about 4.7 by 1022 atoms per second is steeply sensitive to distance from the Sun, ramping up as 32/Atlas gets closer. Even the dust output doesn't tip the scales. Hubble data shows a dust mass loss rate between 6 and 60 kilograms per second. Significant, but not enough to account for the kind of orbital deviation being mapped by astrometric teams. The jets are active. The coma is thick with carbon compounds. And yet, for all this chemical drama, the object's path still refuses to line up with the numbers. The natural engine is running, but it's not moving the needle far enough. The evidence is piling up. Gas alone can't do the job. Something is missing from the standard playbook. 6 years ago, astronomers faced a puzzle that still haunts the field. Oumuamua, that object, barely 400 meters across, shot through the solar system in 2017, moving fast enough to escape forever. But speed wasn't the real shock. As the data came in, something impossible happened. Oumuamua's path bent ever so slightly, away from what gravity alone could explain. Not a wild swerve, but a tiny persistent push. The numbers didn't lie. The residual acceleration, about 17 millimeters per second squared, was real. Yet there was no visible coma, no jets, no dust, just a dry, tumbling shard, accelerating as if nudged by an invisible hand. The headlines came fast. Interstellar visitor accelerates mysteriously. Comet or something else. Theories piled up. Some argued for outgassing. Maybe hydrogen. Maybe something we'd never seen before. Others suggested radiation pressure or even something engineered. But the truth was simpler and more unnerving. There was no clear culprit. Every model left a gap. Now with 3I/Atlas. The sense of déjà vu is hard to ignore. Here's another outsider, this time orders of magnitude larger, showing hints of the same rule-breaking behavior. The difference is scale. A 7M wide object isn't supposed to drift off course so easily. For Oumuamua, a wisp of gas might have done it. For Atlas, the force required is staggering. Yet, astronomers are watching their models unravel again, residuals stacking up in ways that echo 2017's anomaly. What started as a one-off is starting to look like a pattern. Interstellar objects aren't just rare. They're unpredictable. They don't just visit. They rewrite the rules. The shock isn't just that Atlas is drifting. It's that for the second time, gravity alone can't keep the universe on script. Picture the sheer bulk of 3/loss. This isn't a pebble drifting through space. It's a cosmic boulder with mass estimates running thousands of times greater than Oumuamua. The numbers are staggering. Even at the low end, you're looking at a nucleus with several billion tons of inertia. To nudge something like that off course, you need a force that dwarfs what most comets ever experience. For comparison, the Rosetta mission measured jets on Comet 67P that could move a mountain-sized chunk by a few kilometers per orbit. But 3/Atlas is in a whole different weight class. Its mass soaks up momentum like a bowling ball in a sea of ping-pong balls. Every molecule of gas it throws off barely registers. A whisper against a freight train. The usual comet math says more mass, less motion from outgassing. So when orbital modelers see this giant shifting its path in ways the equations can't balance, the problem isn't subtle. The push required to explain the drift would demand outgassing on a scale that just isn't there. Even if every square inch of the surface was erupting, the total force still falls short. This isn't just a matter of tweaking the numbers. The entire momentum budget comes up empty. For an object this massive to move, something big has to be pushing. And right now, all the usual suspects are coming up light. Every established explanation for 3I/Atlas's drift gets stress tested. And every time something doesn't quite fit, if all the usual gas jets and dust outflows can't move this much mass, what's left? Some astronomers point to fragmentation. Maybe a hidden crack split open. shifting the center of mass just enough to nudge the orbit. But there's no evidence for a major breakup. Others wonder if the nucleus is less dense than it appears, a loose rubble pile instead of a solid boulder. But the coma's chemistry doesn't back that up either. Then there's the wild card. Harvard's Abbey Loeb and a handful of contrarians have floated a possibility that sounds like science fiction. What if Atlas is being pushed by something more exotic? Loeb's 23-paper sketches out a scenario where a thin ultralight sail, think a solar sail but on a cosmic scale, could ride on sunlight alone, producing a force too subtle for our current models to catch. The numbers work for Oumuamua, which was tiny and light. For Atlas, with its bulk, the math gets harder, but not impossible if the object is hollow or engineered for maximum surface area. No one in the mainstream is calling Atlas artificial, but the fact that these ideas are even on the table says something about how far this object is pushing the boundaries. When gas can't explain the motion, physics demands another answer. Natural or not, each failed explanation turns up the volume on the question. What exactly are we looking at? And if our models can't handle Atlas, what else out there might be slipping through the cracks? The next chapter in this story is already taking shape. The Vera C. Rubin Observatory, with its 10-year legacy survey of space and time, is about to change everything we know about interstellar visitors. When Rubin comes online, astronomers expect to spot dozens of these objects every year, maybe even more. That means free/loss isn't a once-in-a-lifetime event. It's the beginning of a flood. For the first time, we'll have a steady stream of messengers from other star systems, each carrying clues about where and how they formed. Every new detection brings a chance to catch another rule breaker, another cosmic outlier that doesn't fit the script. But here's the catch. If our models can't even keep up with Atlas, what are we missing from the ones that slip by undetected? The universe isn't just throwing curveballs, it's pitching blindfolded, and we're still learning how to swing. Each anomaly is a reminder that our grip on the cosmos is only as strong as our ability to question it. The more we look, the less the universe seems willing to play by our rules. So, why does any of this matter? Because these objects aren't just passing rocks. They're time capsules from other suns carrying the chemistry and history of worlds we'll never visit. If we want to understand our place in the galaxy, we have to chase every mystery, every unexplained orbit, every outlier that blurs the line between natural and engineered. The next discovery could rewrite everything. If you want to be there when it happens, hit subscribe and tell us what you think 3i/loss really is. On July 1st, 2025, astronomers confirmed the arrival of 3i loss, an interstellar object traveling nearly 60 kilometers per second with a nucleus up to 7 miles wide. Its path was tracked by NASA and the ESA, revealing an orbital shift that standard models of comet physics could not explain. Observations from the James Webb Space Telescope showed a carbon dioxide to water ratio of 8:1 and nickel present without iron, setting it apart from all known solar system comets. Despite decades of accurately modeling comet motion using gas outgassing, the forces measured here were far too weak to account for the deviation, just as with Oumuamua in 2017. The scientific record now holds another case where gravity and jets alone fall short. What drives these anomalies remains unknown. No consensus has been reached and key data are still under review, as sky surveys prepare to detect dozens more interstellar visitors each year. One fact is clear: the rule book for cosmic intruders is not yet complete. Subscribe to stay updated as we uncover what these objects could reveal.
A rare visitor from deep space is passing through our solar system. This object, now officially named 3 Atlas, has astronomers excited. It's a mysterious interstellar traveler moving at an incredible speed of over 150,000 mph and could be as large as 12 meters across, considerably larger than its predecessor, Oumuamua. Telescopes around the world are working quickly to study its unusual glow, trajectory, and the faint haze surrounding it. Some speculate whether it's merely a frozen rock or something far more extraordinary. This massive visitor from another star could hold secrets that might change our understanding of the cosmos. Late June 2025 witnessed an extraordinary event in the night sky. astronomers detected a mysterious object racing through our solar system at a staggering pace. This was no ordinary space rock or comet. It originated from beyond our solar system, making it only the third confirmed interstellar object ever observed. The object, formally named 3I/Atlas, has sparked widespread excitement across the astronomical community. At first, when it showed up in telescope data, astronomers were unsure what to make of it. Was it just an asteroid, a comet, or something completely new? But as more observations came in, it became clear that this visitor did not belong to our solar system. What makes this discovery remarkable is how rare interstellar objects truly are. For centuries, humanity has cataloged thousands of asteroids and comets orbiting the Sun. But objects from other star systems remain an exceptional find. Before 2017, none had been confirmed. Now, with 3I/Atlas, the third such visitor has been discovered within a decade. This isn't just a random space fragment passing through, it's a messenger from a distant star system, carrying clues about worlds we may never physically reach. The story of its discovery, nature, and future path reads like a cosmic detective tale, keeping astronomers glued to their telescopes as it speeds through our solar neighborhood at an astonishing 152,000 mph. The journey of 3I/Atlas began on an otherwise ordinary night between June 25th and June 29th, 2025. The Atlas system, Asteroid Terrestrial Impact Last Alert System, was carrying out its routine task of scanning the night sky for objects that might pose a threat to Earth. Telescopes in Hawaii and South Africa, part of this automated Guardian network, constantly watch the skies day and night, seeking the unexpected. And that's exactly what they found. Initially, the object appeared only as a faint dot moving against the starry background. The system classified it as interesting but not extraordinary, just another object to catalog among the many near-Earth entities. The object was first designated 11PL3Z, a nondescript identifier among countless others. Things took a turn on Tuesday, July 1st, when astronomers observing with a Chilean telescope noticed its unusual behavior. Its trajectory didn't match that of typical solar system objects. It was moving too fast and followed an unpredictable orbit. Follow-up observations on July 1st and 2nd confirmed the suspicions that this object was not orbiting the Sun but merely passing through. A breakthrough came unexpectedly from an amateur astronomer, Sam Dean, who reviewed earlier Atlas images from late June. He spotted the same object in those images, providing invaluable data on its path across the sky. By Wednesday night, the Minor Planet Center, the official tracking body for solar system objects, had received over 100 confirmed observations from telescopes globally. Some astronomers even noticed signs suggesting the object might be a comet due to a faint haze of gas and dust around it. With this accumulating information, scientists felt confident naming it 3I/Atlas. The 3I marks it as the third confirmed interstellar object, while Atlas honors the telescope system that first detected it. Paul Chaz, director of the Center for Near-Earth Object Studies at NASA's Jet Propulsion Laboratory, highlighted the tremendous speed of the object and confirmed its origin from interstellar space. Tracing its orbit backward suggests it approached from the vicinity of the galactic center, proving it originated from another star system, though which one remains unknown. The confirmation of a third interstellar visitor in under 10 years has led scientists to rethink how common such objects might be. Improved technology may finally be allowing astronomers to detect these cosmic wanderers that have likely been passing silently through our solar neighborhood for ages. What sets 3I/Atlas apart from the multitude of other objects zooming around our solar system? First and foremost, its dizzying speed of roughly 152,000 mph. This extraordinary velocity, combined with its size and mysterious appearance, makes it stand out as an exceptional visitor from beyond the stars. This moment offers a rare chance to study matter from another star system, a precious scientific gift arriving across the vast emptiness between stars. Its passage is a cosmic message, inviting us to unlock secrets of distant worlds and the universe beyond our own solar system. Traveling at such an incredible speed, 3I/Atlas could reach the Moon from Earth in just about an hour and a half. This velocity far exceeds that of most objects in our solar system, which move slower because they are gravitationally tied to the Sun. In contrast, 3I/Atlas is merely passing through, scarcely influenced by our star's gravity. Its sheer speed indicates clearly to scientists that this visitor is not native to our solar system. Tracing its path backward reveals it doesn't orbit the Sun like the comets and asteroids familiar to us. Instead, its trajectory points outward toward deep space, likely coming from the direction near the galactic center, though the precise star system it originated from remains a mystery. Its brightness is another puzzle. When Harvard astronomer Avi Loeb examined the data, he found something surprising. 3I/Atlas reflects a significant amount of light for an object from interstellar space. This could mean it either has an exceptionally reflective surface or is enormous in size. If its surface is as dark as typical asteroids, 3I/ would need to be about 12 miles, 20 kilometers, wide to produce such brightness, making it huge compared to previous interstellar visitors. For comparison, Oumuamua was estimated to be roughly 100 meters in length, while Comet Borisov measured about 400 meters across. If current estimates hold, this new object is dozens of times larger than either of those. Another interesting feature is the comet-like behavior observed. Several telescopes detected a faint coma, a hazy envelope of gas and dust around the object, which suggests it could be a comet, although one quite different from those within our solar system. As it approaches the Sun and warms up, it may develop a visible tail, which will help scientists learn more about its composition. Its orbit is unusual too. Most solar system objects move close to the same flat plane, a giant disk with the Sun at its center. But 3I/ plunges through this disk at a steep angle, further confirming it didn't form alongside our planets. The more astronomers study 3I/Atlas, the more they realize its uniqueness. This is no ordinary space rock. It's essentially a time capsule from a distant star system, carrying secrets about worlds we cannot easily visit. Each night as telescopes focus on it, new insights about the universe beyond our solar system emerge. To understand why 3I/Atlas has caused such excitement, it helps to look back at the brief history of interstellar object discoveries. Prior to 2017, humanity had never confirmed a single visitor from beyond our solar system, not one. 4 centuries. All observed celestial objects orbiting the Sun were known to belong here. That changed on October 19, 2017, when Hawaiian astronomers detected an unusual object using the Pan-STARRS telescope. This object, named Oumuamua, meaning scout or messenger from afar in Hawaiian, was unlike anything previously seen. It had a strange shape, either cigar-like or pancake-flat depending on interpretation, and tumbled through space, reflecting sunlight in ways that caused its brightness to fluctuate dramatically. What baffled scientists most was Oumuamua's acceleration as it left the solar system. It sped up slightly, an unexpected behavior since objects normally slow down as they escape the Sun's gravitational pull. This mysterious acceleration sparked intense debate. Some argued it could be caused by outgassing, invisible gas jets acting like tiny rocket engines. Others, including Harvard's Avi Loeb, proposed more extraordinary explanations, including the possibility that it might be an alien light sail or spacecraft. Oumuamua left our solar system quickly, before the most powerful telescopes could fully study it, leaving behind more questions than answers. Then came the second interstellar visitor in August 2019, discovered by amateur astronomer Gennady Borisov. Unlike the enigmatic Oumuamua, this object, named Comet 2I/Borisov in his honor, was unmistakably a comet, showing a visible tail and behaving like those in our own solar system. Borisov was easier to study as it was spotted months before its closest approach to the Sun. Scientists estimated its size to be about 400 meters across and composed of materials similar to comets found in the outer reaches of our solar system. This similarity suggested that comet formation might follow common principles across different star systems. These 2 interstellar visitors provided fascinating but contrasting glimpses into objects from outside our solar system. Oumuamua was strange and unfamiliar, while Borisov seemed familiar. Now, with 3I/Atlas as a third example, there is more data to help scientists determine patterns of what is usual or unusual among these cosmic travelers. The rapid rate of these discoveries, 3 in less than a decade after centuries of none, has led many to wonder if interstellar objects are much more common than previously believed. It's possible that such interstellar objects have been drifting through our solar system all along, and only now have our detection capabilities improved enough to notice them. Following the path of 3I/Atlas reveals a remarkable journey through our cosmic neighborhood. As of early July 2025, it is speeding through space at over 152,000 mph. It is currently located about 3.8 times farther from the Sun than Earth, placing it beyond Mars' orbit but still inside the asteroid belt. Unlike native solar system objects, 3I/Atlas is not orbiting the Sun. Instead, it is traveling on a hyperbolic trajectory, essentially a one-way route that will carry it through our solar system and then back out into interstellar space, never to return. If its path were traced backward in space and time, it would point toward the center of the Milky Way, though identifying the exact star it originated from is nearly impossible. The vastness of space and the millions of years the object may have journeyed make this akin to trying to determine from which cloud a particular raindrop fell. The trail has effectively been lost to time and distance. Looking forward, 3I/Atlas has some notable milestones in its approach. On October 3rd, 2025, it will pass closest to Mars. This will be the first time it nears one of our planets, allowing astronomers to observe any slight gravitational effects Mars may exert on its path. Then, on October 23rd, 2025, 3I/ will reach perihelion, its closest distance to the Sun. Even at this point, it will still be about twice as far from the Sun as Earth. This distance is significant for several reasons. First, the object won't be subjected to intense solar heating that might cause it to fragment if it is a fragile comet. Second, it confirms that 3I/Atlas poses no threat to Earth. Interestingly, Earth itself will be on the opposite side of the Sun when 3I/Atlas hits perihelion. The closest it will approach our planet will occur in December 2025, and even then, it will remain at a safe distance. After this encounter, 3I/ will continue its long journey back to interstellar space, accelerating as it escapes the Sun's gravitational pull. What makes this passage fascinating is that 3I/ is essentially a temporary visitor, a cosmic tourist briefly traveling through our solar system on its eternal journey across the galaxy. It likely formed around another star billions of years ago and has been drifting through the emptiness of interstellar space for millions of years before arriving in our stellar neighborhood. Arriving without warning, it will soon depart, continuing onward to unknown destinations, carrying with it a brief record of its interaction with our Sun and planets, a story that may never be deciphered unless it encounters another advanced civilization capable of decoding it. The discovery of 3I/Atlas represents more than just an astronomical curiosity. It is a treasure trove for scientific research with the potential to transform our understanding of how planetary systems form throughout the galaxy. Until now, the only planetary system we could study directly was our own. Our knowledge of planet formation, asteroid composition, and comet behavior has been based solely on objects originating around the Sun. Now, with 3I/Atlas passing through our cosmic vicinity, we have a real fragment from a distant star system in our hands. It's like being able to pick up a rock from Mars and inspect it without sending a rover. This presents a rare chance to study material created under conditions entirely different from those in our early solar system. What makes this opportunity even more exciting is that 3I/Atlas appears to be significantly larger than our previous interstellar visitors. Its size allows for better observations, more detailed spectral analysis, and potentially a more precise determination of its composition than what was possible with Oumuamua or Borisov. If 3I/Atlas is indeed a comet, as early observations suggest, it gives scientists the rare chance to compare its ice, dust, and gas components with those of comets from our own solar system. Are the same chemicals present? Are their ratios similar? The answers to these questions could help determine whether the building blocks for life as we know it are common across the galaxy or unique to our local environment. Another advantage is that this object was detected relatively early in its journey through our solar system. Unlike Oumuamua, which was already leaving when discovered, researchers will have months to study 3I/Atlas as it approaches the Sun, reaches perihelion, and eventually departs. This longer observation window enables astronomers to coordinate studies using a variety of telescopes and instruments worldwide and in space. The timing couldn't be better from a technological perspective. When Oumuamua passed in 2017, the James Webb Space Telescope hadn't yet launched. Now, with Webb operational alongside other advanced observatories, we possess unprecedented tools to examine this interstellar visitor in great detail. Perhaps more importantly, each newly discovered interstellar object helps answer a fundamental query: how common are these visitors? Before Oumuamua, some scientists estimated that such objects might be seen once every several decades. Now, with 3 confirmed in less than 10 years, those estimates are being dramatically revised. It appears likely that interstellar objects traverse our solar system much more frequently than previously thought, possibly several times per year, with most going undetected because they are either too small or too distant. If interstellar objects are indeed common, it suggests that planetary systems throughout the Milky Way regularly eject material into interstellar space. This, in turn, provides insights into how planetary systems evolve and interact across vast distances and timescales. Despite our advanced technology and brilliant scientific minds, 3I/Atlas holds many mysteries that continue to puzzle astronomers. One of the biggest questions is its exact nature. Is it a comet, an asteroid, or something entirely new? Early observations hint at cometary activity, with a faint fuzzy appearance suggesting gas and dust might be escaping its surface as it warms from the sun. However, it lacks the prominent tail typically associated with comets. Some astronomers propose it could be a pristine comet, one that has never passed close to a star before and thus still retains its original ice. Its unusual brightness also poses a mystery. As Harvard astronomer Avi Loeb noted, 3I/Atlas reflects more light than expected. If it has a dark surface, similar to most asteroids, it would need to be enormous, around 12 miles across, to appear this bright. Conversely, if its surface is highly reflective, it could be considerably smaller. Determining its true size and reflectivity remains challenging even with our best telescopes. Another puzzle is its rotation. While most space objects spin as they travel, measuring 3I/Atlas's rotation rate has proven difficult. Some data suggest it may be tumbling chaotically rather than rotating smoothly on one axis. If true, this might indicate the object experienced a violent event in its past, such as a collision or a close encounter with a massive body that disrupted its rotation. Questions about its age and origin remain open as well. Did it form recently around a nearby star? Or has it wandered through the galaxy for billions of years? Surface features and composition may hold clues, but achieving that level of detail requires observations not yet possible. Perhaps the most intriguing mystery is what 3I/Atlas might reveal about its home system. Every star system leaves signature fingerprints on the objects born within it, unique elemental ratios, specific minerals, and isotopic compositions. If we can decode these signatures, we might learn about a planetary system we may never visit. Some astronomers are also watching for any signs of non-gravitational acceleration as 3I/Atlas travels through our system. Oumuamua exhibited such acceleration, which sparked considerable debate. If 3I/Atlas also shows unexplained accelerations, it could suggest this behavior is common among interstellar objects, rather than a unique trait of Oumuamua. These mysteries make 3I/Atlas far more than just another object to list in catalogs. It is a cosmic puzzle box, with each new observation potentially unlocking another secret about its nature and history, with several months remaining to observe it before it departs our solar system forever. Astronomers hope to solve some of these puzzles before saying farewell to this interstellar visitor. When discussing visitors from beyond our solar system, One question often captures the public imagination. Could it be artificial? Could this be an object created by intelligent beings from another star system? This question goes beyond science fiction speculation. Avi Loeb, one of the most respected astrophysicists globally, has openly considered this possibility, especially after the puzzling observations of Oumuamua in 2017. Loeb famously proposed that Oumuamua might have been an alien light sail or probe, based on its unusual acceleration and peculiar shape, with 3I/Atlas now in the spotlight. Loeb has once again suggested that scientists should use the powerful James Webb Space Telescope to search for signs of non-gravitational acceleration, movement that cannot be explained by gravity alone. If such a force is detected, it could potentially indicate some form of artificial propulsion. However, before jumping to conclusions about alien spacecraft, it's important to recognize that non-gravitational acceleration can occur naturally as well. Comets often exhibit this behavior because when heated by the sun, ice on their surfaces turns into gas, creating gentle thrusts that act like tiny rocket engines. This outgassing can subtly alter a comet's trajectory in ways that pure gravitational models don't predict. What would make 3I/Atlas truly suspicious as an artificial object? Various factors could raise questions among scientists. If it changes direction in ways that defy known physics, emits radio signals or other signs of technology, or has a composition featuring elements or isotopes in combinations that cannot form naturally, these would all be major red flags. Additionally, astronomers are observing whether 3I/ maintains steady brightness or shows consistent patterns in how it reflects light. Natural objects usually have irregular shapes, causing variations in brightness as they spin. A steady brightness might suggest a more regular, possibly artificial, structure. While exploring artificial origins is scientifically valid, history shows that natural explanations tend to prevail. When pulsars were first discovered in the 1960s, their highly regular radio pulses led some scientists to briefly speculate that they might be alien beacons. Today we understand that they are rapidly rotating neutron stars, exotic but naturally occurring objects. Still, the possibility, however remote, that we might be witnessing technology from another civilization adds to the fascination these interstellar visitors inspire among both scientists and the public. It challenges us to confront the profound question: are we alone in the universe? Even if 3I/Atlas turns out to be a natural comet or asteroid, the thorough investigation of all possibilities, including artificial origins, advances our scientific knowledge. As Carl Sagan famously said, extraordinary claims require extraordinary evidence. Although most astronomers find it highly unlikely that 3I/Atlas is artificial, they will undoubtedly be searching for any remarkable evidence suggesting otherwise as it journeys through our solar system. Studying a dark object, possibly smaller than a city, moving at 152,000 mph and billions of miles away requires serious technological capability. And fortunately, we now possess more advanced tools than ever before. Currently, astronomers worldwide are directing all available telescopes toward 3I/Atlas, creating a global effort to understand this visitor before it exits our neighborhood forever. Ground-based observatories in places like Hawaii, Chile, and South Africa track its movement, measure its brightness, and analyze the faint light it reflects to gather clues about its composition. However, the real game changers are our space-based observatories. The James Webb Space Telescope, with its massive 21.3-foot mirror and extraordinary infrared sensitivity, is ideally suited for studying objects like 3I/Atlas. Webb can detect heat signatures and identify specific chemicals and minerals on the object's surface. Astronomers have already secured valuable observation time on Webb for detailed studies of this interstellar traveler. Despite its age, the Hubble Space Telescope continues to provide invaluable data as well. Its ultraviolet capabilities complement Webb's infrared observations, offering a more complete picture across different wavelengths. Together, these space telescopes can reveal details about 3I/Atlas that would be impossible to obtain from Earth's surface. Beyond just observing, astronomers are also listening. Radio telescopes like the Very Large Array in New Mexico and the Allen Telescope Array in California are monitoring for any unusual radio emissions, while no one seriously expects to detect alien broadcasts. These observations help assess whether the object emits any radio waves as it interacts with the solar wind, the continuous stream of particles flowing from the Sun. As 3I/Atlas draws closer to the Sun, it will become more visible, its brightness increasing. If it is indeed a comet, it might develop a more pronounced tail, offering further clues about its nature. This would provide scientists with even more material to study, as the tail contains particles and gases released directly from the object itself. The discovery of 3I/Atlas is viewed by many astronomers as the dawn of a new era in our comprehension of interstellar objects. For all of recorded history until 2017, we had never confirmed a single visitor from beyond our solar system. Now, within fewer than 10 years, we have identified 3. This is not mere coincidence, but rather the result of significant technological progress. Our ability to detect these cosmic travelers has dramatically improved in recent years. Automated sky surveys, more powerful telescopes, and advanced software capable of identifying unusual motion patterns have all played vital roles in this transformation. What we observe now is likely not a sudden rise in interstellar visitors, but rather the emergence of the capability to detect what has always existed. When it begins operation, the Vera Rubin Observatory will take this detection capacity to an unprecedented level. Equipped with a massive camera, it will image the entire visible sky every few nights, effectively creating a cosmic movie that will make spotting moving objects much easier. Experts predict it may discover several interstellar objects annually, possibly even dozens. This expanding catalog of interstellar visitors will enable scientists to answer questions that were previously only speculative. Are most interstellar objects comets, asteroids, or something else entirely? Do they tend to originate from the inner or outer parts of their home star systems? How frequently are planetary systems ejecting material into interstellar space? The answers to these questions will revolutionize our understanding of planetary system formation and evolution. There is increasing interest in the idea of launching spacecraft to intercept interstellar objects, although 3I/Atlas was discovered too late for us to mount such a mission. Several space agencies and private companies are currently developing concepts for rapid response spacecraft that could be launched quickly if another interstellar object is detected early enough. Beyond pure scientific inquiry, these discoveries are shifting our perspective on our place in the universe. Each interstellar object provides a tangible connection to another star system, physical proof that the space between stars is not empty, but traversed by material ejected from far-off worlds. In this way, our solar system is not isolated but part of a larger galactic ecosystem where matter from one star system can eventually become part of another. Thanks for watching this episode. While you're still here, don't forget to click the video on your screen for more quality content.
The object named 3I/Atlas has drawn worldwide intrigue since its initial discovery, becoming only the 3rd verified interstellar visitor to pass through our solar system. Astronomers observed its path for weeks, refining calculations and debating its trajectory. Then came the event that shifted the entire narrative, a subtle yet undeniable change in its motion. Observatories confirmed that 3I/Atlas had defied expectations, redirecting itself instead of following the standard outbound course. The implication could not be dismissed as a trivial error in measurement. This was not simply a frozen fragment drifting from deep space. Guided only by natural orbital mechanics, something far less ordinary appeared to be at work. Under usual circumstances, when interstellar objects enter our solar system, they follow predictable hyperbolic paths. They sweep past the Sun, accelerate outward, and vanish into the void, never to return. That was the case with both Oumuamua and 2I/Borisov, each of which departed silently after their brief appearances. 3I/Atlas, however, shattered this precedent. A deviation so precise against all gravitational models meant that a force beyond solar influence had acted with intention. This sent a wave of unease through the global network of scientists. Natural objects do not simply decide to turn. A course correction suggests purposeful control. And purpose hints at design. Was this an active probe? Some form of propulsion system? Radiation-driven technology? Something beyond our comprehension? The questions multiplied faster than the data could keep pace. The comparison was inevitable. Oumuamua's unexplained acceleration had long been debated, possibly the result of outgassing, though some argued for less conventional explanations. Yet Atlas was different. It did not merely pick up speed. It altered its course in a smooth, deliberate trajectory with that single maneuver. Generations of speculation about alien technology shifted onto center stage. Interstellar remnants are expected to be lifeless wanderers, traveling for eons, scarred by radiation and cosmic collisions, moving endlessly between the stars. But here was an object that rejected that role. Its pivot inward suggested control. Not chance. Telescopic data confirmed it wasn't erratic. Its arc was elegant, precise, as if calculated. That was what sent a chill through research teams worldwide. The possibility that Atlas was mechanical, or at least manipulated by intelligence, was no longer fringe speculation but a serious discussion. Scientific institutions tried to remain reserved, cautiously wording publications while discouraging hasty conclusions. Still, their tone betrayed unease. If this object maneuvered intentionally, then intelligence was involved. Was it a derelict probe still functioning? A fully autonomous machine? Or something entirely beyond our capacity to imagine? What once lived only in speculation about interstellar debris had now crossed into the territory of interstellar craft, a possibility the academic world had resisted for decades. Denial became harder with every updated trajectory. What troubled many most was not simply the redirection, but the silence. Atlas emitted no signals, no transmissions, nothing resembling a beacon. If it was artificial, it was choosing not to speak. That muteness created an unsettling vacuum filled with speculation. Silence could mean secrecy, or worse, indifference. Both were disquieting when applied to a visitor capable of altering course within our sphere. Once the maneuver was confirmed, news rapidly spread from scientific institutions to policy circles and the public. Governments, militaries, and civilians alike all understood that this was not just an astronomical event, it was something that shifted humanity's place in the universe. The most haunting question remained, why return? A wandering rock would not care where it traveled, but a controlled system might have objectives. Did it detect something within our system that warranted closer inspection? Was it gathering data? Or worse, had it interacted with a signal we did not even perceive? Purpose implies intent, and intent reveals planning. Humanity, used to being the cosmic observer, now found itself in the uncertain position of being observed. That shift in perspective rekindled an old debate. How ready are we, scientifically, politically, and culturally, for an encounter with something not born of Earth? Governments and agencies maintain contingency strategies for asteroids, for environmental disasters, and even for conflicts between nations. Yet none possess a true framework to address an interstellar visitor that demonstrates apparent autonomy. The revelation that 3I/Atlas was not simply drifting under the pull of gravity, but moving as if guided sent shockwaves through corridors of power. What if it shifts closer to Earth? What if it is studying us? What if humanity has encountered such things before, only unnoticed? These questions moved instantly from speculative blogs and late-night debates into classified meetings behind secured doors. Astronomers emphasized that its turn occurred without any visible discharge of gas or fragments. Comets vent when their orbits change from solar heat. Asteroids spin erratically. 3I/Atlas, however, glided as though in deliberate grace. Its surface betrayed no violent activity. That composure only made the event more disquieting. If no natural outburst explained its redirection, then propulsion must have existed unseen, or functioned by methods not yet understood. Some speculated about an ultra-thin, invisible sail-like mechanism. Others suggested magnetic interactions. Yet none of these models satisfied the observed reality, for the maneuver bore hallmarks of precision, not accident. For scientists tracking it each night, the experience was overwhelming. Measuring something so small, yet confronting the enormity of what it implied, was to stare directly at history unfolding. To witness a body acting outside the familiar commands of Newton and Kepler was both electrifying and terrifying. They became the first undeniable witnesses to a possibility long whispered in science fiction, that the void may not be devoid of intelligence. And this time it had not passed by unnoticed. It had turned back. That act alone elevated the object from mere curiosity into a kind of silent confrontation. The symbolism weighed as heavily as the astronomy. Humanity has so often gazed outward, assuming the stars would share their mysteries when we were ready. Yet the course change of 3I/Atlas spoke in reverse. It suggested that sometimes the mysteries choose when to reveal themselves, and they do so on their own terms. That redirection was not a simple alteration of momentum. It was a transformation of viewpoint. It shook apart our centuries-old presumption of cosmic solitude. It compelled recognition that the heavens may contain watchers, not merely wanderers, even before further developments. That recognition alone was enough to change cultural thought across the globe. If this was an engineered system, it confirmed we are not the only makers of machines. It would mean humanity may have entered late into a stage that has already been populated. The fear now solidified was that our first undeniable evidence arrived not in greetings or broadcasts, but in a deliberate maneuver. A turn so smooth and silent conveyed its meaning without a single signal. We are present, and we are capable. That revelation is staggering in consequence. Hence, all attention remained fixed on the moment when, in the cold expanse, 3I/Atlas arced away from its expected path, and the weight of new possibilities pressed down on observers around the world. People watched trajectory charts redrawn nightly, their curves bending against every prediction, and felt the collective shiver of realization. This was no longer a passing drifter. It had chosen to return its gaze. Whatever comes next belongs to the future, but its turn alone has already reshaped human perception. The universe, it seems, is not merely filled with drifting debris, but includes deliberate motion, and the proof has been presented before our eyes. When 3I/Atlas redirected, the very rules of orbital destiny were overturned. No longer bound by gravity like every other known body, it acted as though asserting independence from celestial law. In that action, without sound, a message was delivered. Humanity, unready as it may be, has heard it. The familiar night skies have suddenly become places of unease. For generations, the stars represented stability, their reliable motions bringing comfort and order. Farmers gauged seasons by their rise and fall. Navigators plotted their routes beneath their glow, and scientists charted their paths with unwavering trust. Yet now, one solitary gleam defied all assumptions, not merely participating in the cosmic dance, but rewriting its steps. It was as though a painting had shifted within its frame, or a mountain had turned to face its watchers. Something long thought passive had demonstrated intention. The unease provoked by this was as primal as it was intellectual. Observing an immense, unknown entity reverse course was to confront a new fear. Perhaps we were being observed, measured, or even evaluated. Researchers dedicated endless hours in pursuit of every available detail. Infrared scans hunted for emissions, telescopes strained for clarity, and radio receivers scanned the silence for any fragment of signal. Yet quiet persisted, no evidence of a beacon, no trace of a voice. The lack of response was itself a message. Perhaps the visitor possessed technology advanced beyond the reach of current detection, or perhaps our presence held no interest for it. Either theory unsettled those who considered the implications. Mastery that hides itself points to capabilities beyond our own, and apathy, if that were the case, suggested we held no relevance to its objectives. The psychological reverberations spilled far beyond science. Thinkers and artists wrestled with the transformation it implied. For those convinced of humanity's special place in the cosmos, the rerouting of 3I/Atlas was deeply unsettling. Suddenly, intelligence was no longer a uniquely terrestrial phenomenon. It was present, responsive, from across interstellar distances. Others became fixated on questions of intent. Why appear now? Why choose silence? And why here? The movement of 3I/Atlas was no longer purely astronomical. It had become a reflection of our collective hopes and fears. In cities and towns, conversation thrived in public spaces and online forums. Comments ranged from rational discussion to wild conjecture. Some greeted the news as long-awaited evidence that we are not alone, framing it as a scientific breakthrough. Others recoiled, fearing surveillance or assessing the approach as a harbinger of unknown intentions. Creatives responded quickly. Visual artists attempted to depict the enigmatic visitor bending back across the solar system's darkness, while composers set the mood of the event in music both haunting and hopeful. The enigma was too great to dismiss. Simultaneously, divisions formed within the scientific community. Some held fast to the likelihood of natural, if rare, mechanisms, concealed sources of gas, or unexplored physical interactions. Others, more cautiously, considered that deliberate navigation might be the simplest explanation, even if it was the most unnerving. Still others proposed a compromise, even if technology guided the object. Perhaps it had functioned for eons, its systems operating out of habit, not conscious intent. This view, though less alarming, still pointed to the existence of distant builders. Such contemplation inevitably led to governmental concern. Authorities called for briefings and rapid updates from their experts. Military officials mulled over possible responses, recognizing that conventional defense was irrelevant against something so alien. The mere proof that it had redirected triggered high-level secrecy and debate. Was it scouting, posing a threat, signaling more to come? Details trickled slowly from scientific hands to political ones, compounding unease. Faith communities, too, grappled with the implications. Spiritual leaders addressed their congregations, presenting it alternately as a cosmic test, a message, or a source of unity. Some interpreted the event as a welcoming sign, evidence of shared creation. Others felt destabilized, sensing a challenge to established beliefs about human centrality. For some, the confirmation of its return was cause for exhilaration, a nudge that our cosmic tale is connected to broader narratives. For others, it delivered an unsettling shock to old assumptions about isolation and purpose. As time went on, every update on 3I/Atlas's position sparked new analysis. Could its path be deciphered? Was it targeting a specific region within the inner solar system? Each adjustment in its arc became headline material, scrutinized for intent. Careful observers noted that its path was not haphazard. Instead, it conserved energy, directed with the efficiency engineers admire. That precision only deepened suspicions of purpose. Physics rarely writes such clean stories by accident. The curves described by Atlas brought to mind design, not chance. Speculation about its nature and means of movement only grew as the silence persisted. Could it be relying on a propulsion method imperceptible to us, perhaps manipulating space-time directly? Was it drawing upon solar radiation in ways far beyond our crude notions of sails? Some speculated on drives rooted in plasma confinement, exploitation of vacuum energy, or even the bending of gravitational fields themselves. Every idea seemed increasingly speculative, yet all shared the same conclusion: such capabilities lay outside humanity's grasp. To witness an object perform a maneuver that our species could neither reproduce nor even model in detail was a stark reminder of just how far behind we may stand. The academic community erupted in activity. Conferences multiplied, journals overflowed with submissions, and debates once considered fringe surged into mainstream discourse. Periodicals that had resisted technological explanations now contended with an influx of serious papers. Graduate students delivered talks on propulsion systems once relegated to pulp fiction, while senior scholars, long hesitant under fear of ridicule, spoke freely with new boldness. The turn of 3I/Atlas opened a gateway in research culture that would not easily be closed again. Among the general public, reactions vacillated between awe and dread. Amateur stargazers trained personal telescopes toward the heavens, eager for even the faintest view of the enigmatic guest. Every pinpoint of starlight now carried new possibilities. Families debated whether this should inspire anticipation of contact or a deep unease about its intentions. Children questioned their parents about the reality of extraterrestrials, their curiosity echoing the broader uncertainty of society. The event was undeniable in its clarity, a turn so obvious that no skeptic could dismiss it as myth. It was real, and it demanded acknowledgement. Inevitably, media escalation followed. Some networks approached it solemnly, underscoring the profound implications for science and philosophy. Others lean toward dramatization, framing it as a looming threat. Documentaries entered rapid production, while streaming platforms announced adaptations meant to capitalize on fascination. Fact blurred with speculation as the world consumed endless content. Yet beneath the noise, the raw truth persisted. An interstellar object had acted against natural laws, and no rational explanation sufficed. Writers of speculative fiction suddenly found themselves thrust into relevance. For decades, they had conjured stories of probing craft, silent visitors, and first contact. Now those creative imaginings appeared unnervingly prescient. Readers turned to their works not simply for escapism, but as conceptual blueprints, ways to process bewildering reality. The difference, of course, was that fiction permits tidy endings. Reality does not. Reality offered only the relentless tension of a mystery, yet unsolved. Education, too, shifted around the event. Classrooms adopted it as a living lesson, sparking youthful interest in astronomy and physics. Teachers found themselves asked by students whether alien arrival was imminent. Textbooks and curricula were swiftly revised, incorporating not only Oumuamua and Borisov's brief passages, but also this new chapter in which a visitor bent its course deliberately. For younger generations, the universe suddenly stirred with vitality, no longer a fixed backdrop, but an active, enigmatic stage. Perhaps the most striking impact, however, was the dawning recognition of vulnerability. For the first time in recorded history, undeniable evidence showed that something beyond Earth could act within our solar system according to its own will. This was neither a meteorite's blazing descent nor an asteroid's near pass. Those are hazards rooted in chance and governed by prediction. This, instead, was purposeful. It represented not natural accident, but choice. And that realization, that above our skies dwell actors, not mere inert objects, reshaped the very foundation of what security means. Defense was no longer confined to human rivalries or protection from natural catastrophes. It now had to extend to the possibility of intelligence beyond Earth. The timing of this revelation carried its own weight. In an age already marked by technological disruption, environmental crises, and global political strain, the arrival of an object rewriting the rules of celestial order felt like a catalyst. Nations were forced to reconsider their priorities, to recognize that cooperation might not just be desirable, but necessary in confronting a mystery that transcended borders. Against the scale of what loomed above, national lines seemed suddenly inconsequential. The greatest fear sparked by the turn was not solely about the object itself, but about humanity's inability to confront it while divided. As the days gave way to weeks, art sought to capture the sense of upheaval. Murals emerged portraying the enigmatic body as a wanderer bending back to gaze at Earth. Poets found words for the disquiet of being noticed by the stars. Filmmakers drafted visions of silent craft sliding through space, bearing inscrutable intent. Each creative work revolved around the motif of turning back, an act that rendered the universe conscious of us. Amid the flood of speculation, a single truth remained: nothing like this had ever occurred. For millennia, humanity had charted the heavens, recording the paths of comets, asteroids, planets, and stars with growing mastery. Yet never before had an interstellar visitor defied the rules of motion. That singularity made dismissal impossible. It broke the illusion of permanence. From the moment of the pivot, 3I/Atlas ceased being another catalogued waypoint. It became a symbol evoking fear, wonder, and possibility in equal measure. The skies that had once offered predictability now carried profound unease. The implications spread outward like ripples. Science, politics, philosophy, religion, and daily life all bent beneath the weight of its confirmation. Here was evidence that the cosmos was not simply passive, it was active. And it had acknowledged us. Humanity, despite its technological pride, now found itself humbled by what seemed a simple turn in the void. The harmony of planets circling the sun, the clockwork return of comets, the forecastable paths of asteroids, all had reassured generations that the heavens obeyed order. The maneuver of 3I/Atlas shattered that assurance. It was a fracture in the assumed stability of the cosmos, a reminder that, Beneath the surface of predictability could lurk forces and choices beyond comprehension. For the first time, the universe presented itself not as an impersonal system, but as an actor, one with hidden motives. This realization altered the nature of astronomy itself. No longer was it enough to chart orbits and predict alignments. Observation had become witness. Astronomers now spoke of behavior, of intent, of direction interpreted as decision. The language of science crept into realms once reserved for describing life and choice. The boundaries between disciplines began to dissolve. Astrophysicists turned to engineers, asking whether propulsion could be cloaked. Engineers, in turn, consulted biologists about the endurance and repair mechanisms in living organisms, hoping they might illuminate how machines could persist for millennia. Biologists posed questions to anthropologists, wondering what cultures might build such technology and cast it adrift between the stars. One orbital turn had breached all academic walls, igniting conversations across every field of human knowledge. Ethical debates soon followed. If 3I/Atlas represented engineered intelligence, should humanity attempt contact? Was silence safer? Or was dialogue an obligation? Advocates insisted that communication was essential, a chance not to be wasted. Critics warned that broadcasting might expose us to unknown dangers. Between these stances stretched a spectrum of opinion, all sharpened by the undeniable reality that the object had already demonstrated control. Questions of ownership emerged as well. Who had the right to observe, analyze, or engage with it? Should exploration remain open to all, or tightly regulated by governments? The very concept of cosmic territory, absurd on paper, suddenly gained political weight as nations resisted the idea of exclusion from discovery or threat. International institutions were drawn into the debate, but quickly revealed their limits. The event not only highlighted humanity's smallness relative to interstellar mystery, but also exposed the inadequacy of its political structures to respond. Meanwhile, the humanities stepped into unexpected prominence. Historians reminded society of moments when old worldviews collapsed under the weight of discovery, the first contact between distant civilizations, the shock of entire continents revealed, or the Copernican reordering of the heavens. 3I/Atlas had joined that lineage, a disruptive revelation not confined to science, but woven into the story of humanity itself. Across history, pivotal events have redirected the flow of human culture. Many began to argue that the turn of 3I/Atlas could represent such a moment, a hinge on which humanity's story might swing. Scholars of literature explored themes of seeing and being seen, of voyages and homecomings, uncovering echoes of our current unease in myths, epics, and legends stretching back millennia. Psychologists, too, became deeply engaged. Therapists reported patients now raising the phenomenon during sessions, voicing unease about safety, relevance, and the possibility of being watched. People who had once ignored astronomy now dreamed vivid dreams of alien skies. Some embraced it as exhilarating, a sign that possibilities were far larger than believed. Others felt destabilized, spiraling into dread that their everyday lives could not coexist with the enormity of an interstellar enigma. Researchers even coined a new phrase, cosmic anxiety, describing the distinct kind of stress born from the fear of being observed by incomprehensible presences. Speculation about time added further weight to the mystery. If the object was a probe, had it been dispatched eons ago, crossing the gulfs of interstellar space before civilization even dawned on Earth? If that were true, its makers might already have vanished, leaving the craft as their enduring legacy. Or was it dispatched recently, a sign that intelligence elsewhere remains active at this very moment? Both interpretations carry distinct implications. An ancient relic suggested that civilizations rise and fall, leaving behind silent emissaries. A modern probe would imply neighbors alive, capable, and watching. For technologists, the maneuver was humbling. Decades of effort had only placed humanity's devices at the fringes of its own system, while this outsider had demonstrated propulsion feats that evaded not only replication but comprehension. Engineers scoured every fragment of data, hoping for inspiration. The irony was clear. A turn away from departure might itself propel our species closer to the stars. Meanwhile, artists continued their responses, Sculptors carved arcs into stone and metal, capturing the motion of something that would not leave. Playwrights staged dramas featuring unseen travelers, their silent influence permeating each act. Musicians built compositions that soared outward before folding inward again, mirroring the trajectory of the cosmic visitor. Across these media, the recurring motif remained the same: the act of turning back, interpreted as a marker of recognition. Religion, too, deepened its engagement. Pilgrimages formed at observatories, where worshippers prayed beneath telescopes trained on the strange wanderer. Rituals began to include references to heavenly watchers and cosmic interventions. Sermons invoke humility before the enormity of creation, insisting that perhaps humanity had finally been noticed. For some traditions, the news confirmed what they had always suspected, that creation teemed with life and awareness. For others, it destabilized doctrine, forcing reinterpretation of holy texts. Belief communities fractured and evolved in the long shadow of an otherworldly silence that spoke like scripture. Even economics felt the tremor of the event. If 3I/Atlas were a technological construct, did it imply materials, alloys, or mechanisms waiting to be studied, maybe even copied? Reports speculated on industries that could emerge from access to such knowledge. Markets swayed unexpectedly, prices rising and falling on nothing more than rumors about what mysteries the traveler might embody. Its turn alone proved that cosmic movements could ripple across economies as surely as they shook human imagination. Education transformed as well. Universities rushed to establish programs in interstellar studies, hybrid fields that merged astrophysics, anthropology, engineering, and philosophy. Students filled these courses, eager to participate in what seemed to be a new epoch. High schools incorporated lessons on the turning, weaving both scientific explanation and cultural impact into curricula. Young minds spoke of careers in not just science, but in interstellar diplomacy, imagining futures where the unknown might not merely be studied, but spoken to within science itself. The foundations shifted. The traditional search for extraterrestrial intelligence had long focused on signals, listening across the stars for transmissions. But the lesson of 3I/Atlas was stark. Behavior could be a message. A sudden maneuver against predictions carried meaning every bit as profound as a purposeful broadcast. SETI researchers expanded their definitions of communication, treating cosmic anomalies and deviations from natural expectation as valid data in the hunt for intelligence. The realization marked a turning point in perspective. Perhaps the universe did not speak only in words, but in actions. The event revealed human vulnerability in a way that was entirely new. Disasters, pandemics, and conflicts on Earth had always reminded us of our fragility. But these were challenges we understood, rooted in the realm of the familiar. What unfolded with 3I/Atlas was different. The awareness that something not of Earth could act within our solar system introduced a deeper and more unsettling dimension of weakness. For the first time, survival seemed to rest not solely on our choices or natural forces, but on the possibility of decisions made by something alien. For many, that realization was sobering, even paralyzing. Yet alongside fear shimmered the possibility of connection. If 3I/Atlas represented intelligent design, then somewhere, at some point in time, beings had gazed outward at the same stars with curiosity. They had imagined, built, and launched, compelled by the same desire to venture into the unknown. That recognition kindled a strange sense of kinship. Exploration, it suggested, might not be unique to humanity, but a trait woven into intelligence itself. To imagine others who felt that same restlessness to reach beyond their world brought a measure of comfort, even if their silence now left us in doubt. As reflection deepened, it became undeniable that the turn of 3I/Atlas would stand as a marker in human history. Just as the printing press, the telescope, or the splitting of the atom defined eras of transformation, so too would this moment define an age. Generations yet to come would look back and say that this was the time when humanity first witnessed unmistakable evidence that the universe held more than passive rocks and drifting debris. The confirmation of its turn was both a scientific fact and a cultural shift. altering the identity of the species on a planetary scale. And yet, through every argument, every hopeful interpretation, one truth persisted like an unanswered question. 3I/Atlas had offered no explanation. Its silence was total, unbroken, leaving its maneuver as the only form of expression. That enduring quiet magnified all fears and all hopes. In the absence of its voice, humanity supplied its own. Filling the void with imagination, it became at once a symbol, a canvas, and a mirror projecting our dreams, our anxieties, our longing for meaning, and our dread of insignificance. It did not only force us to question what might exist beyond Earth, but compelled reflection on who we are within it. If you enjoyed this video, don't forget to hit the like button and subscribe to our channel. Share your thoughts in the comments about the unexpected turn of 3I/Atlas. We'd love to hear your perspective. Thank you for watching, and we'll see you in the next update.